Okay, so what is a Norton theorem? So Norton theorem is referred to the refers to the any linear electrical network containing voltage sources, current sources, and resistors can be replaced by an equivalent circuit that is consisting of Norton current IN, the short circuit through the load terminals, and the Norton resistance RN. The equivalent resistance seen from the load terminals when all independent voltage sources are replaced by short circuits and all independent current sources are replaced by open circuits. So the Norton equivalent circuit, any current source IN in parallel with the resistor RN. So relationship between Norton and Thevenin relationship, they are dual representation of the same circuit. So their parameters are directly related. IN is equal to Thevenin voltage over the Thevenin resistance. And also the Norton resistance is equal to the Thevenin resistance. So this means the Norton current is the same as the short circuit current. The Thevenin voltage is the open circuit voltage. The resistance are identical. So here we have to short the voltage here 48 volts. And we have to open here we have to short also the RL here to compute for the resistance. For example, here R1 is parallel to R2. Then R3 plus R1 parallel to R2 is 4.667 kilo ohms. So this is R, and this is our Norton resistance. Then the current from the source voltage you see is 48 volts over 12 kilo ohms equal to 4 milliamperes. So the voltage at C is 4 milliohms uh, times 4 kilo ohm equal to 16 volts equal to the Norton voltage. So we have to open first this RL. We use the Thevenin theorem here to find the equivalent Norton circuit here. So the Norton current here is IN over equal to 16 volts over 4.667 kilo ohms equal to 3.428 milliampere. Or if you can use the Norton theorem now, if EV is short, then VC can be found using 48 minus VC over 8,000. So this is the current, entering current. It enters the point C here, and this one is the current from C to A here, and this current is this current is from C to the ground, and this current VC over 2000 is from C to A. So that is equal to 0 by Kirchhoff's load currents. So the VC here is the voltage at C is 6.85714. So IN is found using VC over R3. So R3 is equal to 2 kilo ohms. So this is 6.85714 over 2000. The unit here is ampere. So this is 0.0034287 ampere or 3.4028 milliampere. So this is the equivalent Norton circuit. So we have the IN here. We have the R in the Norton resistance. And we have the R load here. So the IL times R load is equal to IN minus IL times RN here. So it means that the current along the load is IN times RN over the sum of R load and RN. So by Mathematica simulation here, so we have the equivalent resistance of R2 and R3 here. So we have R1, R2, and 3. So we have the given here, and the source voltage here is equal to 48 volts. And the Norton current here is equal to DC short over R3. To calculate the Norton resistance here, Norton resistance R3 plus R1 R R1 times R2 over the sum of R1 R2. So it means here R1 is parallel to R1 is parallel to R2. So the we have the 16 here. So the 16 here is the Norton voltage, and and then 0.0342857 is the Norton current, and the third output here is the Norton resistance, 4.6.67. Okay, so other way of using the Mathematica code here, we have the original current here, original current from the load. Okay, so our Rn here is the Thevenin resistance, R3 plus R1 times R2 over the sum of R1 and R2 here. And I load here, the load current is VTH over the sum of Rn and RL. We use this formula because we have to remember that this we use the original circuit here. So the I load here is equal to VTH over Rn plus RL. Okay, so function to calculate the load current from Norton equivalent. So we have the module here, Norton current. We have the Norton resistance here. The Norton current is 24 over 7 times 10 to the negative 3. So we have calculated the Norton current here, 0.0034287. And we have the uh, Norton resistance here. So the Norton resistance here is the Norton resistance is 466 4,666.7 ohm. And our Norton current here is equal to Rn over the sum of Rn and RL here. So from this formula, Rn over R load plus Rn. Using this formula, so we have the uh, uh, Norton current Rn over Rn plus RL. Then comparison here, we have the table for RL, original current IL, original current for the load current, and we have the uh, load current using the Norton equivalent here. So our RL here is from 0 to 1000. Step 1000. So we have step 1000, 1000 plus 1000, 2000, 2000 plus 1000, 3000, 4000 plus 1000 equal to 5000. But our original uh, current here, original current, from the original circuit, current is equal to 24 over 7. And from the Norton circuit, that is 24 over 7. So if RL is equal to 1000, the current from the original circuit is equal to 48 over 17. And from the Norton circuit, this is 48 over 17. If the load current is equal to 2000, the load current from the load current from the uh, original circuit is uh, 48 over 23. And from the Norton circuit, that is 48 over 23. So this is the load current. We have the figure here. Uh, the of the load current, we have the resistance of the load here. So, for example, here, if we have the uh, our figure, if we have the load current is equal to uh, 0, the corresponding current here is also equal to 0. Now, approximately here for 1,000 here, for example, 5,000 RL is equal to 5,000 here. So the corresponding current from the original circuit is 48 over 29. So this is 48 over 29. So this one also 48 over 29. Okay, so we have the plot now here. So this is the plot of the uh, IL Norton here. IL Norton, the load current here. The plot of the load current versus the load resistance. So where's the IL here? This one, the load current here. Norton IL original. This one for the IL original, and this one is the IL for the Norton equivalent.